Hello everyone, you're welcome to this channel. Today we shall be looking at other details in process modeling and simulation. Precisely today we shall be looking at simulation or modeling and simulation involving chemical reaction as well as convective heat transfer. The last one we looked at was just without chemical reaction, without convective heat transfer. But today we shall be looking at cases involving those scenarios. In many cases or practical cases in chemical industry, there is a need to cool the reactor because it is generated. As a result of that, there has to be a heat exchanger or coolant around the reactor. So let's look at this diagram. If we have a chemical process going on in fluid 1 and it's generating heat, or we need to pass heat into it. So if it's generating heat and we need to cool the heat, so we have to put fluid 2, the second fluid, outside the boundary of its reactor. So that means it has to transfer from the fluid 1 through the wall of the reactor into the fluid 2. So inside the fluid 1, the heat transferring or heat exchange within it will be by convection, as we know. Through the wall or the thick wall of the reactor, it has to be by conduction, heat transfer. Then when it gets to fluid 2 as well, it has to be another convection inside there, and so on. So when we are balancing or modeling for heat energy, so we need to factor this, because not only that it enters into our reactor and goes out, it also can transfer through the wall of the reactor. So when such happens, so what do? We have to consider the heat flow through the wall and the convection heat flow through the fluid 1 and 2. So, but at times we have to simplify things. If the resistance to conduction in wall if the resistance to conduction is very small, that is, the wall is of high thermal capacity and can easily transmit heat, then we can assume that there's no resistance in it. Therefore, the only resistance is found in convective heat flow, so which is through the fluid. Therefore, we can say the heat transfer through the fluid or convective heat flow is equal to UA T minus TC or UA delta T. So where the Q is the convective heat flow, U is the global heat transfer coefficient, and A is the area of convective heat transfer on the surface of the reactor, and that is the temperature difference between the fluid inside and the fluid outside. So there's a convention to that. The convention is that we try to put it in a more definite form, in which case instead of UA T minus TC, where the TC is the temperature of the environment, then we can simply say T environment minus T. And as a result of that, we always put the sign of the heat transfer as positive instead of negative, because it is negative if it is going out, minus, that is because it is going out, just like the convective flow that is going out of the exit of the reactor. So, but if you adopt this convention, there's going to be positive plus UAT environment minus T. So whether the T environment is the one is supplying it, or the heat is going out to the from the inside the reactor to the environment, then we continue to use positive, and we are going to continue to get the same result. Another thing to consider when modeling, another detail of chemical modeling or reactor modeling or process modeling is that involving chemical reaction. So when it involves chemical reaction, then there are some other considerations we have to put. So that means when there is chemical reaction, that means there is, say, a generation time or consumption time in our model. Let's look at this reaction. A convert to B, and the reaction constant is K. So that means the reaction rate is equal to KCA, because if it is reaction of order 1, we need to pay attention to something here. Reactant concentration is mole per meter cube, which is general, but K, which is rate constant, is equal to per second, 1 over second, that is per second. If it is second order, it will change, the unit will change. So, and the reaction rate is always mole per meter cube second, and the order of reaction is there. Now, the point here is that we need to pay attention to the unit that changes, especially for the rate constant, when we are dealing with first order or second order. But one thing is very constant in all of this. What is very constant is that when we are balancing the mass conservation for mass conservation, so mass conservation involving reaction, if it involves reaction, the balance is done in mole, not in kilogram that we were doing before. Balance in mole. We have to perform the balance in mole. So we have to make sure that every term of the expression is expressed or comes down to mole in unit. So please pay attention to this. It's very important. So we are going to look at example there for better illustration. If it is second order, so that means we have A plus B go to C, and the reaction rate is equal to KCA and CB. So one making second order. So in this case, you can see that the reaction rate constant is equal to meter cube per mole second. So we have to balance accordingly. So when you look at in the KCA that we look at earlier, you will see that our reaction rate is equal to KCA, and it means 1 over second here, and this is a mole per meter cube. That means we have to multiply volume to give us meter cube and delta T to give us time, which is a second. So when this meter cube seconds go, we are going to have mole left, so that our rate of our the generation time will give us mole. So we have to multiply R. So that means our mole will be RV delta T. So we have to get our R multiplied by V delta T. So what's our R is equal to KCA. Multiplied by V and delta T will give us our mole. Similarly, our mole in, mole out, mole generated, mole consumed, and the rate of change of mole will also follow similar pattern. So similarly, when we are dealing with a second order, it's going to be like our K has changed in unit, our C remains the same unit, and when we multiply by V delta T, RV delta T, we are still going to get our mole. So that is how we balance. So when our K is changing with temperature, that is, it's a non-isothermal case, then we have to still factor in Arrhenius law, whereby we have to find our changing K variables. So all these are necessary to prepare us for the task ahead. Similarly, when we are modeling in reactor, we have to look at the reactor we are dealing with. This is batch, this is continuous, this is semi-batch. We see in all of these three, we have a mixer, a stirrer that is making all the component uniform in concentration throughout the time. That means in all of these cases, our control volume is uniform. Because it's throughout the tank, the concentration are the same because we are mixing them. But in the case of the tubular reactor, it's not like that because there is no mixer inside. It's a very tiny tube, and it's difficult to actually stir. So as a result of that, what is happening here is different from what is happening here, is different from here, is different from here. So it's not it's a distributed parameter. This is what we call distributed parameter or distributed parameter model, because it's distributed. CA here is different. CA here is different from CA here. Unlike here, where CA is the same everywhere because it is well mixed. So in this case, if it is tubular reactor, we have to find a control volume that is different from the entire reactor. We have to take a narrow piece to serve our control volume. We shall see some illustration later on. So let's look at this example. Develop a mathematical model to represent an adiabatic reactor. The reactor is perfectly mixed and that there is no heat exchange with the environment. This reactor is used to produce component B according to an exothermic irreversible chemical reaction below, A to B to C. A is the reactant, B is the desired product, and C is an undesirable product, which must be removed using separation system to be installed after the reactor. In the beginning, there are no products in the reactor, and the initial temperature and concentration of reactant A are T naught, initial temperature and concentration of reactant A are T naught and Ca naught in mole per meter cube, respectively. Assume that the densities of compound A, B, and C are practically the same and constant with temperature. So it is possible to assume that the volume of liquid inside the reactor remains the same. Use the model to obtain the profile of Ca, Cb, Cc, and T over time. So we are asked to here, in this question, we are asked to develop a mathematical model to represent an adiabatic batch reactor. Adiabatic batch reactor, that means there's no convective heat transfer in this case. Now, and again, we have to obtain from the model Ca, that is concentration of A, concentration of B, concentration of C. That means you have to produce the balance of A, balance of B, balance of C, and balance of temperature. So you have to produce conservation law for the three and temperature energy conservation. So please note all of this. Then secondly, this is a batch reactor. It's not a continuous reactor that we have been dealing with. So that means there's nothing coming in. After the close of the reactor, they put the initial reactant. There's nothing coming in, there's nothing good. Everything happens within. So let's look at how to deal with this case. So after you have understood this step, so we need to produce a balance for A, we need to produce a balance for C, B, balance for C, and a balance for temperature. This energy balance. And I told you, since there's a reaction in this case, in these cases, we have to use balance with mole. Please note that we have to balance with mole because there's a reaction. When there was no reaction in the earlier examples, we use mass, we use kilogram mass. So let's look at A. It's a batch reactor. Note that. So that means in minus out, conservation law here now, plus generation minus consumption is equal to accumulation. All of these are mole. Mole in, mole out, because it is what? It is a reaction system. Mole accumulated. So you have to do it. Please note that. Now it is a batch reactor. Nothing goes in, nothing goes out after the start of the reaction. And A is consumed, not generated. Therefore, it's not generated, A is consumed. Therefore, we have minus consumption is equal to accumulation for A. For B, please remember this. A is consumed, B and C are generated. So for B, it will be the same thing, but it is generated in this case, it's not consumed. So B is consumed, B is generated. That means we have B generated. So this is A consumed, A accumulated. So B generated is equal to B accumulated. Similarly, C generated is equal to C accumulated. Now, for the energy balance, we shall go to that. Let's finish with the mole balance first. So for the A, what is the consumption? The consumption is by reaction. It is consumed by reaction. So we have to do what? We have to use the rate of reaction. As I said earlier, rate of reaction is equal to kCa, which give us mole per meter cube seconds. So this is per second. This is mole per meter cube, and this is we have to multiply by V, which is this one meter cube to cancel this, and we have to multiply by delta T, which will give us second to cancel this, so that we can get more. Therefore, A consumed is equal to minus kCa V delta T is equal to the change in mole of A with time. The change of mole with A with time. That's equal to what? dCAV. CAV what? Mole per meter cube mole. That is the mole dt delta T. The mole dt delta T. So ZAV will be what? That is change in mole within the reactor. So mole dt delta T. So it's mole simply because delta T and delta T cancel in unit. So then when we go to B, similar thing will happen to B. But we look at B. When you look at B, if you look at B, rate of B is equal to 2 kCa. It's equal to 2 of Ra. It's equal to 2 Ra. That is twice twice of A, twice reaction of B is twice the reaction of B. It's twice the reaction of A, The reaction of B is twice because it has, so 1 mole of this react, 1 mole of A react, 2 mole of B is formed. Therefore, it means reaction of B is twice the rate of reaction of A. So that will be used in the B generation for here. So that will be what? 2 kCa V delta T is equal to the change in mode, which is equal to dCBV dt delta T. That is the mole of V in the reactor. Similarly, for the C is the same rate as C. RC is equal to RA because they are in the same mole ratio. R is equal to RA. Therefore, we are going to have kCa V delta T, which is the mole generated for C, is equal to, so we are relating all this rate of reaction of B and C to that of A from the balance reaction. So kCa V delta T is equal to dC CV dt delta T. That is the rate of change of mole of C within. So when we simplify all those, we are going to see that we have dCA dt equals to minus kCa, dCB dt equals to 2 kCa, and dCC dt equals to kCa. So now those are the model representing CA, CB, and CC. CA, CB, and CC. To solve this, we need some initial condition. The initial condition we need here is at T is equal to 0, CA is equal to CA naught. For this one, at T is equal to 0, CB is equal to 0. At this one, T is equal to 0, CC is equal to 0 as well. So which were the condition given? Now, for the temperature term, we are asked to find the temperature term. You remember that. So it's going to be energy in minus energy out plus generation minus consumption is equal to accumulation. So since there's no energy in, it's a batch reactor, no energy goes in, no energy goes out, then there is no energy. We are told that it is, what kind of reaction is this? We are told that it is exothermic somewhere. Let's look for it. Exchange and environment, and the reaction is so we are told somewhere that the reaction, so according to an exothermic irreversible chemical reaction, so look at it, this reactor is used to produce component B according to an exothermic irreversible chemical reaction. So it's an exothermic reaction, so therefore we are having only generation of heat. Energy is only generated, not consumed. So energy generated is equal to energy accumulated. So, and you remember the concept of our energy. To get energy is from MCT of our physics formula. So to get our M, just like before, where we have our So for the accumulation term, we are going to use this concept of physics of MCT, but for the generation term, we are going to do the rate of reaction. Rate of reaction. So multiply by the enthalpy of the reaction. So let's see how this works per se. So for the energy generated, let me erase this. So for the energy generated, we are going to have the rate of reaction, which is RV delta T, which gives us mole, multiplied by the enthalpy, which is joule per mole. So this all of this give us mole, and this all of this give us joule per mole. So that means everything will give us joule. Therefore, so remember, there is a convention that the enthalpy term should be negated, so that if it is exothermic, which is negative, it will be added as generation. If it is endothermic, which is positive, it will be removed as heat consumption. So always remember that. Therefore, R, that means our generation term will be equal to KCA, which is R, KCA V delta T multiplied by minus enthalpy of the reaction. So that gives us our joule. Now all of these we amount to the unit of joule. Then that is now equal to the accumulation time, which is what? The rho, which is MCT. MCT. M is what? Rho V, Cp, and T. dt delta T. So rho V are equal, are constant, and C is also constant. Therefore, we have rho V Cp dt delta T. So, in summary, we are having all of these models put together as what? For A is equal to dCA, for A is equal to dCA dt minus KCA. For B, dCB dt is equal to 2KCA, and for C, dCC dt equals to KCA, and for energy or temperature dTT dt 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 is equal to KCA minus delta HR all over rho Cp. All over rho Cp. So, by looking at all this, we can see that all our models are now assembled, waiting for solution. We have to apply appropriate initial and boundary initial conditions to solve all of them, and we shall be looking at how to solve all of these combined. We have to solve them simultaneously since they are all connected. T is related to Ca, and Ca is related to rate constant, and rate constant can also change with temperature. As a result of that, we have to solve all of them simultaneously in order to be very correct and get the accurate answer. So please stay tuned as we move in the process of modeling and simulation for engineers. Thank you.